colleagues, now I want to discuss a certain question with you. This question has been asked repeatedly, and in our community we've touched on it as well. Why is it that after the diode bridge and the filter capacitor, we suddenly get 310, 320 volts on the electrolytic capacitor, on the input capacitance? Since when we do diagnostics and measure voltages, I always say that we proceed step by step, right? If we're dealing with a switching power supply, and nowadays most modern devices use switching power supplies, then in any case, we first have an input transient input, input diode bridge. That's it. Next, we have exactly this capacitor. And it is on this capacitor that we need to measure the DC voltage, which should be around 310 to 320 volts. So the question is, where does it come from? That's it. Most of you answered correctly. Now let's figure it out together. In reality, in our household power grid, in a regular outlet, it's not 220 volts, it's actually more. So when you measure the voltage with a tester LED, let me show you these examples right away. For example, if we measure the AC voltage with a multimeter, it typically shows us a value of about 300, actually 233 volts. However, guys, this value is what's called the root mean square value, also known as the RMS value. The root mean square value means that the tester automatically multiplies it by a certain coefficient. I'll tell you right away, 0.7. This is the coefficient that's multiplied. So the tester does not show you the true value of the amplitude of this voltage. But what is the root mean square value? The root mean square value is a bit tricky to understand, guys, so I'll try to explain it to you in simple terms, right on my fingers, because the explanation is a little complicated. So for example, let's say you took a light bulb or, I don't know, a motor. Since the shape of our signal is different from a direct current, that is, look, a sine wave is a changing signal. At some point, the value of this sine wave becomes zero. In other words, it has zero potential. Roughly speaking, the efficiency of a direct current signal is much higher than that of a sine wave. And imagine, for example, that you are measuring, say, some signal with a tester, just a pulse, a single pulse. Your tester might show 220 volts, for instance, but the amount of work that a direct current signal can do over a certain period of time cannot be done by such a sinusoidal signal. You see? And that's why, for example, if you take a light bulb and connect it to, say, 220 volts of alternating current and 220 volts of direct current, the bulb connected to the alternating current specifically at 220 volts will glow dimmer. That's why the root mean square value is the value of voltage at which the load will consume the same amount of power. In other words, it is roughly equated to direct current voltage. And that's why if a direct voltage, let's say, for example, a direct voltage of 220 volts is applied, the light bulb will shine brightly. That is, if we connect it. Then, accordingly, if we apply not 220 volts, but 310 volts of alternating current, the light bulb will shine just as it would with 220 volts of direct current. I understand, guys, this explanation might be a bit complicated, but the main thing is for you to realize that this signal, the sine wave, isn't as effective because it changes over time, and at certain moments it has zero potential. That's it. And now, what value is taken? There is a certain coefficient. Why is it called the root mean square value? That is, we divide the maximum amplitude of this signal by the square root of 2. The square root of 2, if you extract it from under the root, is 1.41. And now, for example, when we measure the voltage in an outlet, the tester immediately divides it by 1.41 or multiplies it by 0.7. So if we substitute 1 here and divide 1 by 1.41, we get 0.7. There you go. And we get our original 220 volts. That's it. So I hope, guys, that the concept of the root mean square value is clear, that it's the value at which the load consumes the same power as it would with direct current voltage. Guys, and right away, without going too far off topic, so to speak, I decided to show you a real sine wave from the outlet. So right now, this oscilloscope is connected to the outlet. I'll say right away, guys, it's not recommended to connect small oscilloscopes or, well, large oscilloscopes, that is the non-portable 1S to the outlet, because they use the same ground. In other words, the device could burn out. You need isolation, you need you need to use an isolation transformer. Look, here we have 50 Hertz and we can see a period of 20 milliseconds. And guys, what's most important is the amplitude, or rather, not the amplitude. Well, yes, it's correct to say amplitude, guys. So this value from 0 to the maximum amplitude in one direction to the maximum value is 350. Well, in any case, there are always some inaccuracies. So 350 volts, guys, that's the amplitude. That's it. There is from 0 to the maximum positive value, or from 0 to the minimum negative value. That's it. And the swing is such a concept as the peak value or swing. That's the entire value from the lowest negative point to the highest positive point. So it's this whole part. This is called the swing or peak value. Also in oscilloscopes, there's a concept called peak to peak. So peak to peak voltage means it measures from here to here. If it's from here to here, then it's about 700 volts. That's it. So guys, this is the voltage that we see in the outlet. Now going back to the question, where do these 310, 320 volts on the capacitor come from? Guys, the capacitor charges up to the amplitude value. That is, the amplitude value is the maximum value. So the maximum amplitude value that we saw, yes, those 310 volts. We can look at this on the oscilloscope trace. Here is our sine wave, and here is its maximum value, and the capacitor charges exactly up to this maximum. So when the alternating voltage passes through the diode bridge, we get a pulsating output, yes, pulsating. And this pulsating voltage charges our capacitor. That's it. So it charges our capacitor, and this is exactly the value we see on the capacitor when we measure the DC voltage. I hope that's clear.